Hello everyone, welcome to the second part of our Foundation of Neural Networks session. I call this part the Perceptron classifier. You may not have heard the term perceptron. It's quite famous in computer science. It's a very old traditional approach that, however, is underneath modern neural networks, even still. So let's have a look at that. And in the course of familiarizing ourselves with the perceptron, we will soon realize that, as a matter of fact, this is very close to the logistic regression classifier, which all of us know very well. All right, so let's move on. Here we go. You might remember this picture from the last session, where we basically sketched a simple linear classification problem, a credit scoring type of data set with a bunch of independent variables or features. Two I spelled out, the bureau score and the salary, and our target variable default, indicating whether a lender like John or Sarah or Paul in the past paid back all his or her debt, which means that there was no default equal to no, or whether a debtor failed to repay all the debt. And in that case, we filed a default event. This is indicated by a value of yes in the default column. So we have these two groups, no and yes, defaulters and non-defaulters. We can plot them in a two-dimensional space, and we can use linear classifiers in order to find a decision boundary that separates the data point. For the following, it will be useful to introduce some notation, same notation as before. We have capital X in bold as our data matrix, which consists of row vectors, xi, that live in R2. We have only two variables in this tiny example, and our target is a binary variable, so y is element of 0 or 1. And if you think about it, the classifiers that we've been playing with in business analytics and data science, such as logistic regression, for example, they were linear, meaning that we construct this yellow decision boundary by means of a linear function, where we multiply the elements in our vector x with some parameters beta at an intercept, beta O, and this gives us a linear model. But while this works wonderful for regression, if we face a classification problem, we are not quite there yet. In classification, we have a target variable that is discrete, that is either 0 or 1, and because of that, we typically want to model the probability of our target variable y taking the value of 1, which in my example would mean that there was a default event, given the vector of borrower characteristics given x. This conditional probability is what is typically considered the modeling target in a classification problem. And the way we approach this problem is that, well, it's maybe best to take this equation from the right-hand side. The way we do this, we construct our linear model as in ordinary least square regression, x times beta plus beta O we've got. And we know that no matter what values of beta we will plug in here, this equation will give us some real number, which probably is not in the boundary of 0 to 1 and thus is not a probability. So what we do, we put that through some link function that I denote by g, and if we call the vector of our linear regression, or the result of that, if we introduce the variable z here, and state that z is equal to the output of our linear regression function, then we can state that the value of g, our link function, of that is our prediction from the linear classifier, which I denote as y hat. And given that we choose our link function g wisely, we can be sure that our model output will live in the interval from 0 to 1, i.e. that we will be able to interpret this output as a class probability. So just to remind you, should we choose g to be the logistic function, which just in case was so for the choice of g equal to 1 over 1 plus e to the power of minus z, we obtain our well-known logistic regression. Now we could pick other functions, or we could make other choices for g. We could pick other link functions, and the family of these type of modules is generally referred to as the family of generalized linear models, or GLMs for brief. Generalized in the sense that we have our linear regression, x times beta essentially, but we don't really use that exclusively. We add some functional, like g in my example, and apply this function to our regression output to further transform the output into some target interval that we are interested in, as into the interval 0, 1 for classification problems where we want our model to produce probabilities. Alright, so logistic regression reintroduced. How does that connect to the perceptron? Well, it's very strongly connected because, as a matter of fact, this perceptron thing, which a computer scientist called Rosenblatt invented in 1958, actually is the very same type of model we just revisited. Sometimes the perceptron is defined as a computational unit. It's a thing which can compute, given some input, can compute some output, and it's often depicted in a network type manner. So on the left hand side of my slide you see this network where we have nodes. From left to right we have input nodes, and by the symbols I put into these nodes you can guess that these input nodes just correspond to our data, or more specifically to one data point. And then we have weights. We weight our inputs. We also introduce a special node here, highlighted in gray, which is called, let me see whether I have gray. I probably have, no I don't, well, black will do. So this is called the bias. And we put all that together. We combine the input values, our x, weighted, plus our bias, add everything up. You see the sum right here. And then the result of this input aggregation, this score, you could say, the score that comes out of this operation, we put through some function, some nonlinear function. This is the yellow node, and the S shape inside the yellow node is to sketch that this is some nonlinear function, and afterwards we obtain some output. So the operation of the perceptron is basically an input aggregation, summation, plus added nonlinearity on top of that. And this is exactly what you see on the right hand side, where I use color coding to make this picture most intuitive, or I hope it's pretty much intuitive. And yeah, if you compare that to the previous slide, there is one thing that has changed. We don't use the symbol beta anymore for parameters, but we use W. Obviously this changes nothing. And indeed, the perceptron is pretty much equivalent to logistic regression, or it is better to say the perceptron is equivalent to a generalized linear model. And if we choose G to be the logistic function, then we recover logistic regression, and in that specific case, G equal to the logistic function, the perceptron is indeed equivalent to logistic regression. Well, that sounds a bit awkward, maybe. Why all this terminology, perceptron? Why just, if the only difference is that we have a different notation here? Well, bear in mind that back in 1960s, the dissemination of scientific result was not as it is today, with every new paper coming out of archive just instantly. The special or important innovation connected to the perceptron was an online learning algorithm that Rosenblatt introduced in his seminal papers. Online learning means that giving new data points, given new data X coming in, how can we adapt the weights in this perceptron so as to get an output that agrees with what we want to achieve? How can we update our model when data comes in consecutively so that model predictions, model output remain accurate? That was also part of the perceptron. Otherwise, it would probably not have gotten so famous. But note that from now on, I will make use of this type of notation. We have this computational unit, which is equivalent to a generalized linear model. The free parameters from now on will be denoted by the symbol W, which are indexed by J. Absolutely the same as beta in regression, right? And the perceptron is a combination of a summation operation plus nonlinearity. We always have this sequence. There is an input, X, it's aggregated, it's weighted and aggregated. The resulting signal is put through some nonlinear function, and then we have an output. So this is clearly an input to output mapping, and the nature of that mapping is that we first aggregate and then we add nonlinearity. And this computational unit was later called a neuron, or sometimes it's called a neuron, and then you can guess that many of these guys make up a neural network. And I don't like the analogy of artificial neural network, our computer-based models, and the functioning of the human brain too much, so I won't go there. But if you are interested, you'll find tons of material online, starting with Wikipedia, for example, that will explain you why you can draw some analogy between the way this perceptron model operates and how neurons or how cells in the human brain operate. There is some analogy, but I don't think it's particularly helpful to grasp neural networks or this simple generalized linear model, which, as I said, is just an input to output mapping. I did try to summarize the perceptron a little bit. The perceptron defined. So, as we saw, it is a mathematical function. It's designed as a classifier. So the goal of that function is to help us separate data points of two known classes, like good and bad payers. The type of classifier that the perceptron embodies, we could further categorize as a linear one, because it performs the separation of the data by fitting a line to it, so that data points of different classes live on different sides of our classifier, of our line, or our separation boundary. And where this boundary is located, the shape and orientation of our line, that is determined by some free parameters, W, which you probably were used to denote as betas before. We have these free parameters, and then we need some learning algorithm to determine these three parameters through minimizing some functional, but I'm already jumping ahead. One more note on notation. We have the perceptron here again, and at the bottom in gray, I hope you can see it, but I think it's quite visible. You see the way I was writing down the equation before. Obviously, this input aggregation, the weighted sum, we can write it up as a sum over all the features, but alternatively, we can also make use of the matrix notation. Convince yourself it's just the same thing, right? And the matrix notation is a bit more handy. As we will see that later. What is important right here is that you get used to the matrix notation, that you really internalize this equivalence between the different ways to write down the functions, and I will make use of both ways, writing operations as a sum or using matrix notation, whatever is more convenient in a given context. Maybe since we already are concerned with the matrix notation, it's possibly useful that you spend a little time to convince yourself how this perceptron thing, maybe you still feel it's a little bit bizarre, convince yourself that this is just a linear model. So if you say that out of some magical device we got some parameters, we determined that the weights for our inputs W1 and W2 should be equal to 3 and minus 2. So the 3 is basically just W1 and the minus 2 is W2. I just guessed these values, or maybe they came out of our training. We haven't talked about how these parameters are trained yet, but we'll do so shortly in the next session. And then WO is just our bias. Now we have values. Now we can evaluate the function. For example, in my drawing you see basically the classifier that we would obtain if we were using W1 equal to 3, W2 equal to minus 2, and WO equal to 1. And then we can also just plug in some numbers and play with that classifier. For instance, if you consider a data point 2, O, so x1 equal to 2 and x2 equal to O, you see where it is located. We can evaluate easily the output of our perceptron if we input these quantities. So for these quantities, obviously we get 1 plus 3 times 2 minus 2, that's minus, apologies, times O, which is obviously equal to 7. Now, is there anything special about the value 7? No, there is not. Nothing special about this value. One thing we could possibly point out, or let me color code that a little bit. One thing we can point out is that this value is greater than 0. Please note that for simplicity, I have replaced my nonlinear link function, my g function, just with a linear functional. Note the yellow dot here. Shouldn't use green here, sorry. Black. If I use this symbol, then I mean that it's representing a linear function. Well, you see that when looking at the equations, right? Just make sure to look at the drawings carefully. They are carrying some meaning. Okay. So where was I? Okay, yeah. For this input, x1 equal to 2, x2 equal to 0, we obtain a positive output value from our perceptron. That is not particularly exciting, but equivalently, if we at another data point, let's say we had this one here, where we have x1 equal to minus 2 and x2 equal to 4. And we evaluate our perceptron again. Well, where can I do that? This part of the slide, we evaluate that again. And then we have 1, that's a funny one, 1 plus 3 times minus 2 minus 2 times 4. And, well, you see how this evaluates to minus 1, right? So it's negative. That's the only interesting part. Well, not sure how interesting that is. But the point I'm trying to make is the perceptron, indeed, it is a classifier, because by looking at the sign of our model output, we can easily determine whether a data point that we put into the perceptron is on the left-hand side of our boundary or on the right-hand side. So it really cuts our attribute space, the space spent by x1 and x2 by our data, it cuts it in half. And then we have the upper part and the lower part. Right? So yes, it's a device for classification. For linear classification, and ultimately the purpose of these link functions, the yellow part in the perceptron, which in neural networking terminology are called activation function. I will call them activation functions from now on, which is just the term that we use in the scope of neural networks. And by the way, the reason we call these activation functions is again this analogy that I was hinting at to the neurons in the human brain and how they are activated. These functions are often chosen to be one of these three, either the sigmoid or logistic function or the hyperbolic tangent, or more recently it has become common practice to pick these as the rectified linear unit or ReLU function. And when we reconsider logistic regression, the purpose of our link function, of the logistic function in logistic regression, its purpose is to ensure that the output of our model is bounded by 0 and 1. So we apply a link function in order to ensure that our model output lives in a certain domain, in a certain range of values. And that's absolutely common practice in statistics. And probably this also coined the term link function. In neural networks, and our perceptron is the very first tiny neural network we encounter, slightly different. The main purpose of this function is to introduce non-linearity. And you see in this example with the three popular choices for the activation function that they are all non-linear. And you also see their derivative. So one take home that we will need a little later is that these activation functions are differentiable. And you see the derivatives here and how they behave. Don't worry too much about that right now. Just note we'll need that later. So ultimately their purpose is to introduce nonlinearity. It's a bit hard to show this in a model that is as simple as the perceptron, but we'll see it very soon. Now, in the reminder of this subchapter, I just put some exemplary code using Python to play with linear models, with some artificial data, and also with logistic regression. Here, for example, I would generate data using two Gaussians. We have two classes, positive and negative, in red and in blue. And we generate data points for each class using a multivariate Gaussian distribution with some mean vector and some standard deviation then we can fit a classifier to this data, and the fat black line that you see here is a result of fitting a logistic regression to our artificial data. And you see that in this case, where we have data coming from two Gaussians with different means and different covariance matrices, it's very easy to fit that data with a linear model. But if we generate some more complicated data, here I'm using a Python function that is part of this machine learning library or framework, scikit-learn. The function is called makeMoons. If you look very carefully, you can maybe see it, makeMoons. That is just a ready-made Python function that generates data in this shape. Obviously here, the pattern that would distinguish the positives and the negatives is no longer as nice as before, and it's not really possible to linearly separate our data. And if we fit a logistic regression to that data, we again get some decision boundary, but it's not really a nice one, and we make a couple of errors because our classifier is unable to capture the more complicated relationship between our two inputs, x1 and x2, and the class label. And as a little sneak preview, once we make our way to neural networks, we can build more complicated models that are then very able to fit this more complicated data and various other types of data. Before moving on, just to remind you that example here I took from a blog post that's called NN from Scratch. The previous ones are available, the previous examples are available for you to play with. Should you be interested, you have the URL down here. Maybe we can have a quick look. So here's our GitHub repo, right? Humboldt-WI Wirtschaftsinformatik /Adams. And within this repo we have our exercises, or we will soon have our exercises. And the codes that I use in the lecture is in the folder lecture codes. And then if you navigate to that folder and then session 2 code examples, sometimes it takes a little, here is our notebook. Well, we haven't had a tutorial session yet, but maybe you're already familiar with a little bit of Python. I'm importing some standard libraries for plotting and also to create my logistic regression model. Here are our activation functions. If you want to play a little bit with the activation functions, you have a code here. There is the hyperbolic tangent, there is the ReLU function. Here is the example where we generate some data and fit it by means of a linear model. Here's the data with the two Gaussians, where I make use of some functionality in the NumPy library of Python. This little NP here, it stands for NumPy, and then we have a class random, and that class knows the method multivariate normal, and it allows us to create data points sampled from a multivariate normal distributions with some mean vector and covariance matrix, which I just define here, and then I generate 100 data points for each class. And if you look carefully, you will note that I construct the parameters of my normal distribution such a way that one class has a mean vector that is centered at 0, x1 equal to 0 and x2 equal to 0, and the other is slightly different. We have x1 equal to 1, x2 equal to 2, and also the two covariance matrices that I defined differ a little bit. So one class, it's the former one, x1, has some more variance. the data spreads out a little bit, and you clearly see that here among the blue points, how they spread out a little bit more than the red points, which are more condensed, which stick together, so to say. So maybe a nice example, if you're in YouTube Python, how to generate some data and fit a classifier to that data. And then here is the example where we use the ready-made functions makeMoons to generate some data. And once we have the data, we can again fit some order to it using logistic regression. Here's the call to logistic regression. And then I'm defining a functional here, plot decision boundary, which color codes which takes care of the color coding of our graph to highlight how it's cut in half by our logistic regression classifier and how every data point on the upper side is classified as belonging to the red class and how every data point on the lower side is classified as belonging to the blue class. Yeah, and you already see that we can now move on to neural networks, which is exactly what we have on our agenda. So back to the slides. This is where we're, and now we will put multiple perceptron classifiers together, and in doing so we construct our very first neural network.